Somewhere above you right now, a clock is running slow. Not broken, not malfunctioning. Running slow because of where it is and how fast it is moving. Right now, at this moment, the satellites threading orbits above your head are ticking through time at a different rate than the clock on your wall. The difference is 38 microseconds per day. That sounds small. It is not small. Without corrections built directly into the software, every GPS system on Earth would drift by roughly 11 kilometers every single day. Your phone would send you into a field. Aircraft would miss runways. The entire architecture of modern navigation depends on engineers accounting for the fact that time does not pass at the same rate everywhere. That is not a theoretical concern. That is an engineering requirement baked into infrastructure that billions of people use without thinking about it. This is where it starts. Not with black holes, not with spacecraft approaching the speed of light, with your phone giving you directions. Time is the one thing every human being experiences as universal. It ticks. It moves forward. A second is a second whether you are standing in a kitchen in Ohio or floating in orbit above the Pacific. That is what it feels like. That is also wrong. Completely, verifiably, measurably wrong. Time runs at different rates depending on how fast you are moving and how deep you sit in a gravitational field. These are not philosophical positions. They are physical facts confirmed by experiment, encoded into satellite design, and measured in the bodies of astronauts. When astronauts return from long missions aboard the International Space Station, they are measurably younger than they would have been if they had stayed on the ground. Not metaphorically, not in the sense that space travel is hard and they feel older. Younger by the count of actual elapsed seconds. The station moves fast enough that time aboard it passes slightly slower than time on Earth's surface. The difference over a 6-month mission is about 5 milliseconds. That is a small number. It is also a real number, confirmed repeatedly by atomic clocks. It means that the traveler and the person who stayed home have now lived through a different quantity of time despite starting their lives together. Take that effect and drag it towards something more extreme. Near a black hole, the curvature of space-time becomes so severe that time dilation stops being a matter of microseconds. An observer watching someone fall toward a black hole's event horizon would see that person's movements slow. Their light would stretch and redden. And at the horizon itself, from the outside observer's perspective, the falling object would appear to freeze, to stop, not to cross over. Time, from that distant vantage point, would appear to cease flowing for anything at the edge. The universe produces this, not in theory, in the actual fabric of space and time that everything, including you, is embedded in right now. What this video will go through is the physics that makes all of this true, from Einstein's 1905 insight that the speed of light is constant for all observers, to the rubber sheet curvature of space-time, to the atomic clock experiments that turned equations into measurements you can hold in your hand. But more than the how, the thing worth sitting with is what it actually means. Time is not a river flowing at a constant rate through a fixed and universal channel. It is personal. It is local. It bends. And every clock in existence, including the biological one running inside you, is moving through time at a rate determined by physics that most people never think about for a single moment of their lives. But the stranger truth is not that this happens. it is how completely it changes what time actually means. For most of human history, nobody thought to question whether time could behave differently depending on where you were or how fast you were moving. That question simply did not exist. Time was time. It moved. It passed. A second was a second, whether you were standing in a field in England or sailing toward the horizon or sitting in a cave somewhere in the dark. The idea that this could be otherwise, that a clock on a ship and a clock on shore might genuinely disagree, would have struck virtually any thinker before the 20th century as not just wrong, but meaningless. Like asking whether the number 5 weighs more in Paris than in Rome. This was not a failure of imagination. It was a reflection of experience. Every human being who has ever lived has felt time moving at the same steady rate. You wake up, hours pass, you sleep. There is no sensation of time accelerating or slowing. There is no moment when the clock on the wall and the clock in your chest seem to drift apart. The rhythm feels built-in, universal, shared by everything that exists. The sun rises, it sets, the seasons turn. None of it suggests that time could be anything other than a single river, flowing at the same pace everywhere, carrying all of reality along with it. This intuition runs so deep, it is almost impossible to see it for what it is. Language itself is built on it. When you say something happened simultaneously with something else, you are assuming that simultaneity is a fact, that there is a real answer to the question of whether two events happened at the same moment. When you ask how old something is, you assume age means the same thing regardless of where or how that object has been moving. These are not conclusions anyone reached after careful reasoning. They are foundations so basic that questioning them feels like questioning whether language itself makes sense. Isaac Newton formalized all of this in the late 17th century. His framework, which organized physics for over 200 years, built time into the mathematics in the most straightforward possible way. Time was a background parameter, absolute, universal, flowing forward at a constant rate that nothing in the universe could alter. Newton was explicit about this. He called it absolute, true, and mathematical time, and described it as flowing equably without reference to anything external. The phrasing is careful. He meant that time did not depend on matter, motion, or anything happening inside it. It was the stage on which physics performed. The performance could be fast or slow, chaotic or orderly. The stage never changed. This picture had enormous explanatory power. It worked. You could take Newton's equations, plug in positions and velocities, and predict where planets would be decades into the future with extraordinary accuracy. The math was consistent. The predictions matched observations. Nothing in the experiments of the 17th, 18th, or 19th centuries gave any hint that time might be doing something more complicated underneath the surface. If absolute time was an assumption, it was an assumption that never once seemed to fail. What would it mean if Newton was right? Two clocks, separated by any distance, moving at any speed relative to each other, would always agree. You could carry a clock to the far edge of the solar system and bring it back, and it would show exactly the same elapsed time as an identical clock you left behind on Earth. You could fly one clock around the world 1,000 times, and it would still tick in perfect lockstep with the clock sitting on the ground. Gravity would not matter. Speed would not matter. Position would not matter. Time was just time, everywhere, always, for everything. This is still how most people think about time, not because they have studied Newton, but because it matches every experience they have ever had. It matches the way clocks work in daily life, the way schedules function, the way memory is organized. Past, present, future, arranged in a single clean line, the same line for everyone, marching forward at 1 second per second. No ambiguity, no exceptions. The 19th century added one complication. Physicists studying electricity and magnetism eventually arrived at equations describing the behavior of light. James Clerk Maxwell worked out in the 1860s that light was an electromagnetic wave, and his equations predicted a specific speed for that wave, roughly 300,000 kilometers per second. The problem was that the equations did not specify what this speed was measured relative to. In Newton's framework, that had to mean something. Speed is always relative to something. A ball thrown on a moving train travels at one speed relative to the train and a different speed relative to the ground. Everyone assumed light had to work the same way, so physicists went looking for the medium light traveled through. They called it the luminiferous ether, a substance filling all of space, stationary, providing the reference frame against which light's speed could be measured. The idea seemed reasonable. Waves need something to wave through. Sound needs air. Ocean waves need water. Light, they assumed, needed the ether. In 1887, Albert Michelson and Edward Morley ran an extraordinarily precise experiment designed to detect Earth's motion through this ether. As Earth moved through space, they expected to find slight variations in the measured speed of light, depending on which direction it was traveling relative to Earth's motion. They found nothing. The speed of light appeared the same in every direction, regardless of how Earth was moving. The ether did not seem to be there. Physicists spent years trying to explain this result without abandoning the ether. They proposed that objects contract slightly in the direction of motion. They built elaborate mathematical frameworks to preserve the old picture. Some of the finest minds of the era worked on it. None of the solutions were satisfying. None of them changed the underlying equations in a way that felt truly coherent. The result was a physics that was technically functional in most cases, but quietly unsatisfied with itself, carrying a splinter it could not remove. That was the world into which Einstein stepped in 1905. He was not working at a university. He was not surrounded by colleagues debating the ether problem. He was, by most accounts, thinking about something more fundamental, what it would actually mean, physically, for the speed of light to be constant for every observer everywhere. He followed that question where it led. When Einstein arrived, that entire picture came apart in a way nobody saw coming, and nobody has been entirely comfortable with since. In 1905, Albert Einstein was a 26-year-old, working a desk job at a patent office in Bern, Switzerland. He was not a professor. He had no laboratory. He had no research funding and no team of colleagues to bounce ideas against. What he had was a problem that had been quietly unsettling physicists for years, a problem so fundamental that most people in the field had simply agreed to ignore it. Einstein did not ignore it. He followed it to the end, and what he found there changed everything Newton had built. The problem was light. Specifically, it was the speed of light. In the late 1800s, James Clerk Maxwell had worked out the mathematics of electromagnetic waves and arrived at a startling result. His equations predicted that light traveled at a fixed speed, roughly 300,000 kilometers per second. Not fast, but a specific, exact number that fell out of the equations whether you wanted it to or not. This bothered people immediately, because in Newtonian physics, speeds are relative. If you throw a ball at 30 kilometers per hour from a train moving at 100 kilometers per hour, someone on the platform sees the ball moving at 130. Speeds add. That is how the world works. So whose frame was Maxwell's speed of light measured from? Was it relative to something? Was there a medium it traveled through, the way sound travels through air? Physicists invented a substance called the luminiferous ether and spent years trying to detect it. They never found it. Experiments kept returning the same maddening result. The speed of light appeared identical regardless of how the observer was moving. The ether wasn't there. The speed didn't change. Nobody knew what to make of that. Einstein decided to take the results seriously, not to explain it away, not to assume the experiments were wrong. What if the speed of light really was constant for every observer, regardless of their motion? What would that actually mean? He sat with this question and built an entirely new framework around it. In 1905, he published the paper that introduced what we now call special relativity. It rested on two postulates. The first was that the laws of physics are the same for every observer moving at a constant velocity. There is no special frame, no privileged position. A scientist running an experiment on a moving train and a scientist running the same experiment in a stationary lab should get identical results. The second postulate was the radical one. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Always 300,000 kilometers per second. Every time. No exceptions. Read that again. A light beam fired from a spaceship moving toward you at half the speed of light does not arrive at you any faster than a light beam fired from a stationary source. The spaceship's speed does not add to the light's speed. You still measure that light arriving at exactly 300,000 kilometers per second. This seems impossible. It violates everything intuition says about how velocity should work. But experiment after experiment has confirmed it. It is simply true. And from that single strange truth, the entire structure of special relativity follows inevitably, like pulling one thread and watching the whole fabric rearrange itself. Here is the problem that falls out immediately. If light always travels at the same speed, and speed is distance divided by time, then when two observers in different states of motion measure the same beam of light, they cannot both get the same answer unless something else is adjusting. Distance or time must change between them. Einstein's insight was that both do. Space and time are not fixed backgrounds against which events happen. They are flexible. They compress and stretch depending on how the observer is moving. And for time specifically, the consequence is this. A clock that is moving relative to you ticks more slowly than a clock sitting still beside you. Not because of some mechanical effect on the clock. Not because the vibrations of the clock are disturbed by motion. Time itself passes at a different rate. This is what physicists call time dilation due to motion, and it is one of the most disorienting conclusions in all of science. The effect is not noticeable at ordinary speeds. At the speeds humans have ever traveled, even in the fastest spacecraft ever built, the difference in clock rates is so small it requires atomic clocks to detect. But the mathematics is unambiguous about what happens as speeds increase. At 10% of the speed of light, roughly 30,000 kilometers per second, Time dilation is there but tiny. A clock moving at that speed runs slower than a stationary clock by a factor of about 1.005, 0.5%. Barely measurable, essentially invisible. Push the speed to 50% of light, and the factor climbs to about 1.15. Time on the moving clock runs roughly 15% slower, still relatively modest. But the relationship is not linear, it accelerates. At 90% of the speed of light, time dilation becomes dramatic. A clock moving that fast runs at less than half the rate of a stationary clock. For every 2 seconds that pass for a stationary observer, fewer than 1 second ticks by on the moving clock. At 99% of light speed, the factor hits 7. Time on the moving clock is running 7 times slower than for the stationary observer. And at 99.9% of light speed, the factor climbs past 22. For every 22 seconds the stationary observer experiences, the moving clock records just 1. The curve does not level off. As you approach the speed of light, the time dilation factor shoots toward infinity. A clock actually traveling at the speed of light would, from the perspective of an outside observer, stop entirely. Time on it would not pass at all. This is part of why nothing with mass can reach the speed of light. As you approach it, the required energy increases without limit, and time dilation becomes total. What Einstein was describing was not a measurement error. It was not a trick played by the finite speed of light on distant observers. The time difference is real. If you send a clock on a high-speed journey through space and bring it back, it will show less elapsed time than a clock that stayed behind. Not because the traveling clock was jostled or disrupted, because it genuinely passed through fewer seconds. The clocks will disagree, and they will be right to disagree, because they were on different paths through space-time, and those paths carry different quantities of time. This has been verified experimentally, not just in thought experiments, with real clocks on real vehicles, and the numbers match what Einstein's equations predict with extraordinary precision. There is something worth sitting with here. Newton's universe had absolute time. Every clock in the cosmos, if it were perfect, would tick in unison. Time was the one thing everyone shared, regardless of where they were or how fast they moved. Einstein's universe has no such shared clock. Two observers in relative motion are not just disagreeing about time. They are living through different amounts of it. There is no referee, no cosmic standard that tells you which clock is right. Both are right, locally. Both are measuring real elapsed time for their own path. The disagreement is not a problem to be resolved. It is the nature of time itself. This was not a small adjustment to the existing picture. It was a demolition. And Einstein arrived at it not through experiment, not through new instrumentation, but by asking what happens if you simply take the constant speed of light seriously and follow the logic wherever it goes. Motion, Einstein said, does not just change your position, it changes your time. To understand why motion slows time, you need one specific thought experiment, not a metaphor, not an analogy, a thought experiment that strips the problem down to its bare mechanics and makes the conclusion feel, for the first time, genuinely unavoidable. Once you see this, you cannot unsee it. The strangeness stops being abstract. The setup is almost absurdly simple. Imagine a clock. Not a clock with hands and gears, but a clock that works by bouncing a single pulse of light, a photon, back and forth between two mirrors. one mirror on the floor, one mirror on the ceiling. Every time the photon completes one round trip, the clock registers one tick. That is the entire mechanism. A photon, two mirrors, and a count. This clock keeps perfect time because light moves at a perfectly constant speed. Every tick takes the same amount of time as every other tick. No friction, no wear, no error. Now, you are standing next to this clock. It is stationary. You watch the photon travel straight up to the ceiling mirror, bounce back down, hit the floor mirror, and return. Up and down, up and down. Clean vertical lines. The path the photon takes is the shortest possible distance between the two mirrors. It is doing the least work it can do to register each tick. Here is where it gets strange. Put the clock on a train. The train is moving sideways at high speed, but the clock itself is still ticking exactly the same way from the perspective of a passenger sitting next to it. From inside the train, nothing has changed. The photon still travels straight up and straight down, still registers a tick each round trip. No different from before. But now you are standing outside the train, watching it pass. From your position on the ground, the mirrors are moving sideways as the photon travels. The photon is not just going up and down anymore. From your perspective, it is tracing a diagonal path. It bounces off the floor mirror, travels upward and to the side, hits the ceiling mirror, travels downward and to the side, returns to the floor mirror. A triangle, or more precisely, a zigzag pattern stretched out in the direction of the train's movement. The diagonal path is longer than the vertical path. This is not a matter of opinion. Geometry forces it. If the mirrors have moved sideways between the photon leaving and arriving, the photon must have covered more distance than just the vertical gap between them. Now hold both facts in your head at once. The photon traveled a longer path as seen from outside the train. The photon still traveled at exactly the speed of light, because the speed of light does not change. It cannot. That is the foundational axiom Einstein started with, and every experiment ever conducted confirms it without exception. The photon does not speed up to compensate for the longer distance. The speed of light is fixed. Here is the problem. If the photon covers more distance at the same speed, it takes more time to complete each round trip. Each tick of the clock, as measured from outside the train, takes longer than each tick as measured from inside the train. The two clocks, the one you are holding on the ground and the one on the train, are no longer in agreement. The moving clock is ticking slower. This is not a malfunction. Nothing has broken. No one has tampered with the mirrors. The clock on the train is doing exactly what it has always done, but the tick rate, as measured by an outside observer, has decreased. The moving clock runs slow. Were you watching carefully for the sleight of hand? There isn't one. The logic is airtight. A longer path at a fixed speed means more time per tick. The only way for the speed of light to remain constant for both the observer on the train and the observer on the ground, which the physics demands, is for time itself to run differently between them. This is the moment the strangeness becomes undeniable. Now comes the piece that matters most. Some people, hearing this for the first time, think, all right, interesting, but this is clearly a quirk of this peculiar light-bouncing clock, a mechanical trick. A normal clock, one with gears, springs, electronics, would not behave this way. It would keep ticking at the same rate regardless of what the photon was doing. That instinct is wrong. and understanding why it is wrong is the whole point. Any physical process that takes time is ultimately built on cause and effect. One event triggers the next. An electron moves and a current flows. A chemical bond forms and breaks. A neuron fires. Whatever the mechanism is, it depends on something happening. And that something happening depends on the propagation of physical influence, which cannot travel faster than light. The light clock is not a special case. It is the clearest picture of a constraint that applies to everything. If the light clock slows down, all clocks slow down. All timekeepers, all physical processes. That includes the chemical reactions that keep neurons firing, the electrochemical signals running through a body, the molecular processes of aging. If a person were on that train, every biological process in their body would slow relative to an observer watching from outside. Not because of any medical effect of travel, not because of stress or discomfort, but because the universe does not grant an exception. The speed of light is the speed limit on causality, and causality is the mechanism behind every change that has ever occurred. What the light clock reveals is not a quirk. It is the operating principle of reality. Motion stretches the path that any physical process must follow. The universe cannot let you cheat the speed limit, so it slows the clock instead. Every clock, every process, every cell, the clock has not malfunctioned. Time itself has slowed down. The strangest implication of special relativity is what physicists call the twin paradox. Though calling it a paradox is slightly misleading. It is not a paradox. It is a prediction. A clean, testable, repeatedly confirmed prediction that happens to feel deeply wrong the first time you encounter it. The reason it feels wrong is that it forces a conclusion most people resist. Two people who began life at the same moment, on the same day, in the same hospital, can end up genuinely different ages. Not because of illness, not because of chance, because of the path each of them took through space. Here is the setup. Two identical twins, born at the same instant. One of them climbs aboard a spacecraft and accelerates to a velocity close to the speed of light, say 90%. The other stays on Earth. The traveling twin flies out toward a distant star, reaches it, turns around, and comes back. When the spacecraft lands and the two twins stand face to face for the first time in years, they are not the same age. The one who traveled is younger, measurably, biologically, physically younger. Fewer cells have divided, fewer heartbeats have passed. Less time, in the most literal sense, has gone by for them. Now here is why this feels like a paradox. Special relativity tells you that motion is relative. There is no privileged frame of reference. From the Earth twins' perspective, the spacecraft is moving away at 90% the speed of light. But from the spacecraft twins' perspective, it is the Earth that is moving away at 90% the speed of light. If the situations are truly symmetric, if each twin is equally entitled to say the other one is the moving party, then shouldn't each twin see the other's clock running slow? And if both clocks are running slow relative to each other, how can one twin come back genuinely younger? Shouldn't they be the same age when they reunite? This is where the resolution cuts through. The situations are not symmetric. They were never symmetric. The Earth twin sits in one place for the entire duration of the journey. They experience no acceleration. Their velocity, relative to everything around them, remains essentially constant. The traveling twin does not have that luxury. To leave Earth, they must accelerate. To reach the distant star, they travel at high speed. To stop at the star, they must decelerate. To come back, they must turn around and accelerate again. To land back on Earth, they must decelerate a final time. The traveling twin undergoes multiple episodes of acceleration that the Earth twin never experiences. Acceleration is not relative. This is the key fact. When you push on the gas pedal in a car, you feel it. You press back into your seat. There is no ambiguity about which object is accelerating. The car is, not the road. In the same way, the traveling twin feels every burst of thrust, every change in velocity. The Earth twin feels nothing. The asymmetry is real and physical. It is not a bookkeeping trick. The moment the traveling twin fires their engines to turn around at the distant star, the symmetry between the two situations is broken completely, and it cannot be restored. What happens during that turnaround is the critical part. When the traveling twin reverses course and begins heading back toward Earth, something changes in how they account for simultaneity. From their new reference frame, the Earth twin's clock appears to jump forward. Not because anything weird happens to the Earth twin directly, but because the traveling twin has shifted from one reference frame to another. The accumulated difference in elapsed time between the twins builds during this phase. The outbound leg, the inbound leg, and especially the turnaround together produce a net result. The traveling twin has passed through fewer seconds of time than the Earth twin by the time they land. How much fewer? That depends on the speed and the distance traveled. At 90% the speed of light, the Lorentz factor is roughly 2.3. A round trip to a star 4 light-years away takes a little over 8 years from Earth's perspective. The traveling twin experiences that journey in something closer to 3.5 years. They return roughly 4.5 years younger than their sibling, not 4.5 years behind in news and events. 4.5 years younger in the cellular, biological, physical sense. Their body has run through 4.5 fewer years of chemistry. Push the speed higher, and the effect becomes even more pronounced. At 99% the speed of light, the same round trip leaves the traveling twin nearly a year older, while the Earth twin has aged more than 8 years. At 99.9%, the gap widens dramatically. The direction is always the same. The traveler comes back younger, always. This is not a thought experiment that exists only on paper. The underlying physics has been confirmed repeatedly with real equipment. Muons, which are subatomic particles produced when cosmic rays strike the upper atmosphere, travel toward Earth's surface at speeds close to the speed of light. Their natural lifespan is short, roughly 2 microseconds. At the speeds they travel, they should decay long before reaching the ground. They do not. From our perspective on Earth, their internal clocks are running slow. They last long enough to be detected at sea level because time is genuinely passing more slowly for them. The traveling twin experiment, scaled down to a particle the size of almost nothing, plays out thousands of times every second in the atmosphere above you. The Haffel-Keating experiment in 1971 brought this even closer to human scale. Physicists loaded cesium atomic clocks onto commercial airplanes and flew them around the world. When the airborne clocks were compared to clocks that had stayed on the ground, they had ticked differently. Not by much, but by exactly the amounts that relativity predicted. The effect was real, measured, and matched the equations. Bring this back to the twins. Two people with the same DNA, the same birthday, the same starting point. One of them decides to move through space in a dramatically different way than the other. That decision, and nothing else, determines that they will not be the same age when they meet again. There is no force acting on them, no disease, no accident, simply the path each of them took through space-time. The universe does not treat all paths equally. Some paths through space accumulate more time, some accumulate less. The geometry of space-time rewards the traveler, in a narrow sense, with fewer seconds elapsed. The emotional weight of this is hard to sit with. Somewhere in the logic of a constant speed of light is the conclusion that time is personal, that it belongs to you and your particular trajectory through the universe, that your twin, standing still while you flew, lived through more of it. The traveling twin arrives home genuinely, biologically younger, not by illusion, not by measurement error, but because fewer seconds actually passed for them. There is a precise mathematical relationship between speed and time, and it has a name. Physicists call it the Lorentz Factor, represented by the Greek letter gamma. It is, at its core, a multiplier, a single number that tells you exactly how much slower time runs for a moving object compared to something sitting still. When you hear that a traveling twin ages less, or that a particle shot through an accelerator lives longer than it should, the Lorentz factor is the equation doing the accounting. It is not an approximation. It is not a rule of thumb. It is the precise, calculable ratio between two clocks running at different speeds, and it works every time. The formula itself is not complicated to state, even if the implications are staggering. You take the object's velocity, divide it by the speed of light, square the result, subtract that from 1, take the square root, and then flip it. The number you get is gamma. At low speeds, gamma is so close to 1 that you would never notice the difference. Drive a car at highway speed your entire life, and the accumulated time dilation over decades amounts to something smaller than the width of an atom. The universe is keeping track. You would never know. But watch what happens as the speed climbs. At 10% the speed of light, gamma is about 1.005. Time on the moving object runs 0.5% slower. Barely a rounding error. At 30% the speed of light, gamma reaches roughly 1.05. Still modest. At 50%, things start to shift. Gamma hits approximately 1.15, which means a clock moving at half the speed of light runs about 15% slower than a stationary one. A journey that takes a year by one clock takes only 10.5 months by the other. That gap is real. That is not an illusion of measurement. 15% of a year is nearly 7 weeks of time simply not happening for the faster traveler. At 70% the speed of light, gamma is around 1.4. At 80%, it reaches roughly 1.67. At 90%, it jumps to 2.3. This is where the curve starts to behave differently. Doubling your speed from 45% of light to 90% does not double the effect. It more than doubles it, and then some. The relationship between speed and time dilation is not linear. It accelerates. At 99% the speed of light, gamma is approximately 7. A clock moving at that speed runs 7 times slower than a stationary one. A mission that lasts 7 years by Earth's count would feel like 1 year to the crew. That is not a small correction to pencil in at the bottom of a calculation. That is a fundamentally different experience of time for two sets of people watching the same journey from different frames. At 99.9% the speed of light, gamma reaches roughly 22. At 99.99%, it climbs to about 70. Were you to push an object to 99.999% the speed of light, gamma would be over 200. The faster you go, the steeper the curve climbs. The returns on additional speed become increasingly extreme. Each fraction of a percent closer to the speed of light produces a larger jump in gamma than the fraction before it. This is why no object with mass can reach the speed of light. Not because of some arbitrary rule, not because of a technical limitation waiting to be engineered around. It is because reaching light speed would require gamma to become infinite. An infinite time dilation factor. An infinite energy requirement. The math simply refuses to allow it. As you accelerate a massive object toward the speed of light, the energy required does not increase steadily. It increases without limit, faster and faster, approaching infinity as you approach that final speed. The universe has set a hard ceiling, and the Lorentz factor is the equation that describes exactly how hard that ceiling becomes as you push against it. Particles in accelerators live out this math daily. A muon, a subatomic particle produced when cosmic rays strike the upper atmosphere, has a natural lifespan of about 2.2 microseconds. At rest, it would decay almost immediately after being created, long before it could reach the ground. But muons created high in the atmosphere are moving at a large fraction of the speed of light. Their Lorentz factors are high enough that from Earth's perspective, their internal clocks run dramatically slower. They live long enough to reach the surface. Physicists measure this. They count the muons that arrive. The numbers match the predictions of the Lorentz factor precisely, every time. This is what separates the Lorentz factor from a clever theoretical construct. It is predictive. You can calculate gamma for any speed, make a precise prediction about what an experiment should measure, run the experiment, and watch the numbers come back in agreement. This has been done in particle accelerators around the world, across different energies, different particles, different experimental setups. The formula holds. It has never been found wrong. The precision matters because it transforms time dilation from a philosophical curiosity into something you can engineer around. The GPS calculations discussed elsewhere in this series depend on exactly this kind of precision. The corrections are not estimates. They are derived from the Lorentz factor and from general relativity, applied to specific speeds and altitudes, producing specific numbers that engineers bake into satellite clock frequencies before launch. The math works because the universe is consistent, and the Lorentz factor captures exactly how consistent it is. There is something almost uncomfortable about how clean the curve looks when you plot it. For most of the speed range you could ever imagine traveling, gamma barely moves. It sits just above 1, patient, almost unnoticeable. Then, as you approach the speed of light, it bends upward sharply, then more sharply still, racing toward a value that can never actually be reached. What it shows is that time dilation is not a gradual and gentle effect. It is a curve that accelerates sharply toward infinity as you approach the speed of light. Special relativity handles motion. It describes what happens to time when things move fast. But in 1905, Einstein had already sensed there was more. He had solved one piece of the puzzle and left the other one sitting on the table. Gravity. The force that holds you to the ground, keeps the moon circling the Earth, pulls planets around stars. Newton had described it for more than 2 centuries, a force reaching invisibly across space, tugging at everything with mass. It worked. The equations were accurate. Satellites could be tracked. Cannon trajectories could be calculated. The orbits of planets matched the predictions almost perfectly. For 200 years, nobody had a reason to question it. Then Einstein started thinking about what gravity actually was, and the answer he found in 1915 was one of the most disorienting ideas in the history of science. Gravity, he concluded, is not a force at all. It is a shape. More precisely, it is a curvature in the fabric of space-time itself, produced by the presence of mass and energy. Imagine a rubber sheet stretched tight and flat. Place a heavy ball in the center. The sheet sinks beneath it, forming a depression, a curve in the surface. Now roll a smaller ball across the sheet. It does not travel in a straight line. It curves toward the heavy ball, following the contour of the depression. From a distance, it looks like the small ball is being pulled by a force, but it is not being pulled by anything. It is simply following the geometry of the surface it is moving through. Einstein said, the universe works the same way. Mass curves space-time. Objects follow that curvature. What Newton called gravitational force is actually the natural path of motion through warped geometry. This is general relativity. The rubber sheet image is useful, but it undersells the strangeness badly. Because the rubber sheet only shows the bending of space, the full reality is stranger. Mass does not just curve the spatial dimensions of the universe, it curves time as well. Space-time is a single unified fabric, and mass warps every part of it. When you are sitting deep inside a gravitational well, close to a massive object, time itself runs more slowly for you than it does for someone farther away. Not your perception of time, not your psychological experience of time passing, the actual rate at which time moves. Clocks in stronger gravitational fields tick measurably slower than clocks in weaker ones. This is gravitational time dilation, and it follows directly from the geometry of general relativity. Here is the concrete version. Take a building, a tall one. Place one atomic clock in the basement and another on the roof. Both clocks are identical. Both are running in the same city, at the same temperature, under otherwise identical conditions. Wait long enough, and the 2 clocks will no longer agree. The clock in the basement will be running slightly behind the clock on the roof. Not because of any mechanical difference, not because of vibration or temperature or anything mundane. Because the basement is closer to the center of the Earth, sitting deeper inside Earth's gravitational field, experiencing stronger space-time curvature. Time genuinely passes more slowly there. This is not a thought experiment anymore. It has been measured. The difference is tiny by human standards, measured in fractions of nanoseconds. But it is real, and it matches the predictions of general relativity precisely. Were we observing the star's final collapse as it unfolded? That question felt enormous. This question feels quieter, but lands just as hard. Is time actually running slower in your basement than in your attic? Yes, it is. The difference is too small to notice without atomic clocks, but it is there, happening continuously in every building on Earth, at every moment. The effect grows as the gravitational field grows stronger. Earth's gravity is modest by cosmic standards. The effect becomes dramatic near much denser objects. But even on Earth, the effect is real and measurable. Gravity bends time the same way a prism bends light. It cannot help it. That is what mass does to the geometry of space-time. Why does this happen? The intuitive answer requires accepting one thing completely. Space and time are not separate categories. They are dimensions of a single structure. When you move through space, you are also moving through time, and the rate at which you move through time depends on the geometry of the space-time around you. Near a massive object, the geometry is compressed, curved. The time dimension gets, in a very real sense, squeezed inward. An observer far from the gravitational source, sitting in flatter space-time, moves through time at a faster rate. They watch the clock near the massive object and see it ticking slower. The person near the massive object is not malfunctioning. They are simply moving through a region where time has been stretched thin by mass. Think about what this means for altitude. A clock on Earth's surface sits closer to Earth's center than a clock in orbit. The surface clock is deeper in Earth's gravitational well. Space-time there is more curved. Time runs slower. The orbital clock, sitting in weaker gravity, runs faster. The difference between a clock on the surface and a clock in low Earth orbit amounts to about 45 microseconds per day from the gravitational effect alone. That is not a rounding error. That is a measurable, confirmed, engineered around consequence of general relativity. Satellites in orbit have to account for it. The precision required by modern navigation systems depends on getting this number right every single day. But there is a complication. Special relativity and general relativity do not take turns. They run simultaneously. An object in orbit is both moving fast and sitting at a higher gravitational altitude than the surface. Special relativity says the orbital motion slows the satellite's clock. General relativity says the weaker gravity at altitude speeds it up. The two effects push in opposite directions. The final answer depends on which effect is stronger in any given situation, and that depends on the specific speed and altitude involved. For GPS satellites at 20,000 kilometers up and moving at roughly 14,000 kilometers per hour, the gravitational effect wins. Their clocks run faster overall relative to ground clocks by about 38 microseconds per day after both effects are combined. For the International Space Station, which is lower and faster, the velocity effect is larger. Its clocks run slightly slower than ground clocks. Different orbit, different answer. Same equations. This is what makes general relativity so consuming to work with. The two mechanisms of time dilation are always both present, always pointing in potentially different directions, and the outcome in any specific case requires careful calculation. Near the surface of a planet, gravity dominates. At high speeds near light, velocity dominates. In the most extreme environments in the universe, near neutron stars and black holes, the gravitational effect becomes so powerful that no amount of velocity can compensate. Time near those objects runs at rates that have no analogy in everyday experience. The math still describes it. The intuition breaks. What Einstein built in 1915 was not just a new theory of gravity, it was a new theory of time itself. Newton had said gravity was a force. Einstein said gravity was a consequence of geometry. Newton had said time was absolute. Einstein said time was local. Wherever there is mass, time bends around it. A planet does not just hold objects in orbit by pulling on them. It runs time slightly slower in its vicinity. And that variation in time is part of what we experience as gravitational attraction. Everything falling toward Earth is following the natural curve of space-time geometry, bending toward the region where time runs most slowly. The apple does not fall because it is pulled. It falls because it is following the curvature that mass has carved into time. Gravity, Einstein realized, was no sheer force pulling objects together. It was time itself running at different rates in different places. The question that kept physicists up at night in the mid-20th century was simple. How do you test any of this? Einstein's equations were elegant, the logic was airtight. But physics does not run on elegance, it runs on evidence. And time dilation, as a phenomenon, presented a brutal experimental challenge. The differences it predicted were not just small, they were almost insultingly small. At the speeds humans travel, and at the gravitational differences humans experience, the gap between clocks was measured in microseconds, nanoseconds, fractions of a second. No mechanical clock, no spring-wound timepiece, no pendulum in a tower could detect a difference that fine. To test relativity, physicists needed something that had never existed before. They needed a clock that was essentially perfect. Atomic clocks are that thing. The basic principle is strange the first time you hear it. Rather than counting the swings of a pendulum or the oscillations of a quartz crystal, an atomic clock counts something much more fundamental. Atoms of certain elements, when exposed to specific frequencies of microwave radiation, transition between two energy states at an extraordinarily stable rate. Cesium-133, the element used in most atomic clocks, resonates at exactly 9,192,631,770 cycles per second. That number is not approximate. It is the definition of a second in modern physics. 1 second is defined as 9,192,631,770 oscillations of a cesium atom. These clocks do not drift by more than a billionth of a second per day. Some modern optical lattice clocks are so precise they would not gain or lose a single second over the entire age of the universe. That is the instrument you need if you want to catch time dilation in the act. In October of 1971, two physicists named Joseph Haffel and Richard Keating did something that sounds almost absurd. They booked seats on commercial airline flights and brought atomic clocks with them as carry-on luggage. 4 cesium atomic clocks flew eastward around the world on passenger jets. Then another set flew westward. The entire time, identical cesium clocks sat on the ground at the United States Naval Observatory, ticking away as a baseline. When the airborne clocks came back, Haffel and Keating compared the readings. The differences were tiny. We are talking about hundreds of nanoseconds, but the differences were there, and they matched what Einstein's equations predicted to a precision that ruled out coincidence. The eastward flying clocks lost time relative to the ground clocks. The westward flying clocks gained time. The direction mattered because Earth itself is rotating, which changes the effective speed of the airplane relative to a non-rotating reference frame. Both effects, the special relativistic slowing from velocity and the general relativistic speeding from altitude, were embedded in the results. The experiment worked. Was there skepticism? Of course. The margins were tight enough that some critics questioned whether the measurement uncertainties swallowed the signal. But the experiment was repeated, refined, and extended over the following decades with increasingly precise instruments. Each time, the results came back the same. The predictions held. The clocks that moved faster through space ticked more slowly. The clocks that sat higher in Earth's gravitational field ticked faster. Both effects were real. Both effects were measurable. Both effects were exactly what Einstein had calculated. Then the measurements got stranger, more intimate in a way. Starting in the 2000s, physicists at the National Institute of Standards and Technology in Boulder, Colorado, began using a new generation of atomic clocks so precise they could detect time dilation not between cities, not between continents, but between floors of the same building. In one experiment, they placed two optical atomic clocks at different heights inside their own laboratory and simply waited. One clock sat roughly a foot higher than the other. That is not a metaphor for anything dramatic. 1 foot, the height of a large house cat, the distance from your knee to the floor. And after enough time had passed, the clocks disagreed. The higher clock had ticked faster. The lower clock had ticked slower. The difference matched the prediction of general relativity for that specific elevation change, accounting for the precise difference in gravitational potential between those 2 points in space. Think about what that actually means. Time is not running at the same rate at your head and your feet. The geometry of space-time is warped enough by Earth's mass that the few feet separating the top of your body from the bottom produce a genuine, measurable difference in the rate at which time passes. You cannot feel it. Your neurons are nowhere near sensitive enough to notice a difference of a few parts in 10 to the 17th power. But it is happening, right now, in the room where you are sitting. The floor is in a slightly deeper gravitational well than the ceiling, and time down there moves just a little more slowly. Not by enough to matter in any practical sense for daily life, but by a real, physical, experimentally verified amount. This is what atomic clocks revealed. Not just that Einstein was right in some abstract mathematical sense, but that the universe is continuously doing something quietly extraordinary at scales humans can barely fathom. Every object on Earth is experiencing slightly different rates of time depending on its elevation. The roots of a tree age at a different rate than the tips of its branches. Technically, unmeasurably to any biological instrument, but genuinely, according to the laws that govern the structure of space-time itself. The NIST result was not a laboratory curiosity that physicists filed away and forgot. It was a proof of concept for something the GPS system would have to contend with as an engineering reality. It was the universe refusing to be abstract any longer. The Haffel-Keating experiment told us that time dilation followed clocks onto airplanes. The NIST building experiment told us it followed clocks off the shelf and onto a table. The effect does not require a particle accelerator. It does not require a rocket or a black hole or any exotic condition at all. It requires only mass, and Earth's mass is more than sufficient. Physicists spent decades chasing time dilation with instruments sophisticated enough to catch it. What they found was that it was never hiding. It was just waiting for a clock precise enough to see it. The clock at the bottom of the building ticked slower, not by much, but by exactly as much as Einstein said it should. Every time you ask your phone for directions, you are relying on time dilation corrections that run automatically in the background. This is not a metaphor. It is not a loose analogy borrowed from physics, to make technology sound more interesting. The correction is real, it runs constantly, and without it, the entire GPS network would fail within minutes in a way that accumulates into catastrophic errors before the end of any given day. Time dilation is not an exotic phenomenon reserved for thought experiments about twins and spacecraft. It is baked into the infrastructure of modern civilization. Engineers had to account for it. They did. And now it runs quietly underneath every navigation app on every phone on the planet. Here is the setup. The global positioning system depends on a constellation of satellites orbiting Earth at roughly 20,000 kilometers above the surface. Each satellite carries an atomic clock, extraordinarily precise, counting oscillations of cesium atoms at a rate measured in billionths of a second per day. GPS works by measuring time. Each satellite broadcasts a continuous signal stamped with the exact moment it was sent. Your phone receives signals from multiple satellites simultaneously, computes the tiny differences in arrival time between them, and uses those differences to calculate distances. From those distances, it triangulates your position. The entire system depends on the satellite clocks being synchronized with clocks on the ground to within roughly 20 to 30 nanoseconds. A nanosecond is 1/1000th of a second. The margin is that tight. Any drift beyond it, and the calculated distances start to go wrong. And distances that go wrong mean positions that go wrong. Now here is where the physics arrives as a problem. Those satellites are moving at approximately 14,000 kilometers per hour relative to the surface of Earth. That is fast enough that special relativity applies in a meaningful, measurable way. According to special relativity, a moving clock runs slower than a stationary one. At 14,000 kilometers per hour, the satellite clocks tick about 7 microseconds per day, more slowly than identical clocks sitting on the ground. 7 microseconds does not sound like much, but GPS navigation calculates position from signal travel times, and light travels roughly 300 meters in 1 microsecond. 7 microseconds of clock error translates to about 2 kilometers of positional error per day from the velocity effect alone. That would already be a serious problem for a system supposed to be accurate within meters. But the velocity effect is not the only effect hitting those satellites. The satellites also sit 20,000 kilometers above Earth's surface. Up there, they are farther from the center of Earth's mass. Gravity is weaker, and according to general relativity, weaker gravity means time runs faster. A clock at higher altitude, sitting in shallower gravitational potential, ticks faster than a clock down on the surface. For the GPS satellites, this effect works in the opposite direction from the velocity effect, and it is larger. General relativity pushes the satellite clocks about 45 microseconds per day faster than ground clocks. Two effects, opposite directions, different magnitudes. Net result, the satellite clocks gain approximately 38 microseconds per day relative to clocks on the ground. 38 microseconds, every day, without correction. Were we watching a slow catastrophe build? Yes. Light travels about 11 kilometers in 38 microseconds. That means uncorrected satellite clocks would introduce positional errors that compound at roughly 10 to 11 kilometers per day. A navigation system accurate to within meters would, without relativistic corrections, guide you into the wrong city before the week was out. The implications were stark and unavoidable for everyone involved. An uncorrected GPS network would not slowly degrade into inaccuracy over months or years. Instead, it would fail catastrophically and almost immediately from any practical standpoint. Engineers running simulations in the 1960s and early 1970s, as the system was being designed, understood this fundamental constraint with crystal clarity. The mathematics of relativistic effects were not speculative or merely theoretical. They were deterministic, measurable, and they demanded a working solution before construction could proceed. There was no margin for approximation or hope that the effects might somehow cancel out in practice. The system either accounted for relativity, or it simply would not work at all. This is not a theoretical concern that physicists flagged and engineers quietly dismissed. It is a concern that engineers took seriously enough to build the correction directly into the hardware before the first satellite ever launched. The solution is elegant. Rather than correcting after the fact in software, engineers detune the satellite clocks before launch. On the ground, the atomic clocks oscillate at their natural resonant frequency. Before being placed into orbit, their frequency is deliberately slowed, adjusted from 10.23 MHz down to 10.22999999543 MHz. The difference is tiny, but it is precisely calibrated so that once the satellite is moving at orbital velocity in the weaker gravitational field it occupies, the combined effect of special and general relativistic time dilation brings its tick rate back into alignment with ground clocks. The satellite leaves Earth running slightly slow by design, and physics corrects it into accuracy once it reaches orbit. What makes this worth sitting with is the chain of logic it required. Einstein published special relativity in 1905. He published general relativity in 1915. For much of the 20th century, these were regarded as theoretical physics, important, verified in the laboratory, but remote from everyday technology. When the first GPS satellites launched in the 1970s, some engineers debated whether relativistic corrections were even necessary. The effects sounded small. The debate was settled quickly. The numbers were unambiguous. Build in the correction, or accept that the system does not work. They built in the correction. Every aircraft using GPS navigation is flying on corrected time. Every shipping container tracked across the ocean by logistics software is located on corrected time. Every self-driving vehicle prototype that uses GPS to orient itself is doing so on corrected time. The correction runs below the level of any user interface. Nobody sees it. Nobody manages it. It simply operates invisibly as a consequence of the universe being structured in a way that Newton did not anticipate and Einstein described precisely. There is something worth pausing on here. The GPS system is the most widely used practical application of general relativity in human history, and most people who use it daily have no idea the connection exists. They open a map, tap a destination, and follow a blue arrow through traffic. Somewhere overhead, a satellite clock is ticking at a frequency that was adjusted on the ground to account for the curvature of space-time. The satellite does not know this. The phone does not announce it. The universe does not offer a notification. But the correction is there because it has to be. Reality does not accommodate ignorance of its own rules. GPS engineers learned that in the 1970s, did the mathematics, and quietly embedded one of Einstein's stranger predictions into every device that has ever asked a satellite what time it is. Without relativity built into the software, your phone's map would be wrong by roughly 11 kilometers every single day. The International Space Station is traveling at roughly 28,000 kilometers per hour, circling the Earth about 16 times every day. That is not an abstraction. That is real hardware, real metal and glass and wiring, moving fast enough to lap the entire planet before most people finish a work shift. And at that speed, something happens to time aboard the station that no passenger notices, that no crew member feels, that registers on no human sense whatsoever. Time runs slow up there, not much, but measurably, provably, in a way that Einstein's equations predicted decades before anyone could build a clock sensitive enough to confirm it. The numbers are worth sitting with. Special relativity says that the velocity of the ISS, that 28,000 kilometers per hour, causes time on the station to pass roughly 0.007 seconds slower every 6 months compared to clocks on the ground. 7 milliseconds. The gap between a camera flash and the moment your eye registers it. But there is a second effect pulling in the opposite direction. The station orbits at approximately 400 kilometers above Earth's surface, where gravity is slightly weaker than at the ground. Weaker gravity means time runs faster, not slower. General relativity says that higher altitude should push the station's clocks ahead by a small amount each day. So you have two competing effects. Velocity slows the station's time. Altitude speeds it up. The velocity effect wins. The net result is that ISS astronauts accumulate slightly less time than their counterparts on Earth. Over a standard 6-month mission, the difference works out to roughly 5 milliseconds. 5 milliseconds. That is the number. And here is what that number actually means. An astronaut who spends 6 months aboard the ISS and then walks back onto Earth has lived through approximately 5 fewer milliseconds of existence than every person who stayed on the ground during that same window. Not a figure of speech, not a way of talking about perception or biological wear. 5 milliseconds of actual elapsed time simply did not happen for them. The universe ran a slightly different clock for them while they were up there, and when they came back down, the clocks compared, and the difference was real. What makes this more than a theoretical curiosity is that it has been confirmed repeatedly with hardware. Atomic clocks have been flown aboard the station and synchronized with identical clocks on the ground before launch. After months in orbit, the clocks are compared. The station clock reads behind. Not randomly behind, not slightly off due to instrument drift, but behind by almost exactly the amount Einstein's equations say it should be. The margin of agreement between theory and measurement is tight enough that any remaining discrepancy is swallowed by the uncertainty of the clocks themselves. The clocks agree with Einstein. They have never failed to agree with Einstein. The physics here demands nothing more exotic than the basic mechanics of orbital motion and spacetime's geometry. Gravity curves both space and time in ways that defy ordinary human intuition. The precision required to measure this rivals the finest atomic experiments ever conducted. Yet the station was never designed as a relativity laboratory. It simply orbits, and the clocks aboard measure what truly happens up there. This touches something deeper about how the universe truly operates. Understanding time dilation at human scales forces a complete reckoning with reality. The astronauts themselves, moment by moment, remain slightly chronologically adrift from Earth. This is the piece that catches people off guard. Time dilation sounds like something that lives in textbooks and thought experiments, in twin paradoxes and light clocks that exist only on chalkboards. Then someone points at an actual orbiting laboratory with actual crew aboard and says, "It is happening there, right now, to real people." There are astronauts in orbit at this moment who are aging fractionally slower than you are, not because of anything unusual about their biology, not because space preserves them in some exotic way, because the geometry of space-time treats a fast-moving object in a weaker gravitational field differently than it treats a stationary object in a stronger one. This is not a side note in the physics. It is the physics expressing itself in living tissue. No astronaut notices it. That is the part worth emphasizing. There is no sensation of time slowing, no dreamlike heaviness to the hours, no awareness that the clock on the wall is ticking at a rate that disagrees with every clock on Earth below. The human nervous system has no instrument capable of detecting a 5-millisecond discrepancy across 6 months. You would need something far more precise than a biological brain. You need cesium atoms oscillating billions of times per second, compared against other cesium atoms oscillating billions of times per second. That is the only instrument fine enough to show what is actually happening. And when you use that instrument, what you find is a gap. Small, steady, exactly where Einstein said it would be. Were this effect to compound over years instead of months, it would accumulate. An astronaut who logged 2 years of total mission time, not unreasonable for career astronauts, would return to Earth having experienced roughly 20 milliseconds less of existence than peers who stayed on the ground across those same years. Still a tiny number. Still far below anything a person could sense or experience. But measurable, documented. A real asymmetry in how much of their lives they have actually used up, embedded in the cells and the atoms and the clocks they carried with them through orbit. Time dilation is usually framed as a curiosity for extreme conditions. Black holes, near light speed travel, the event horizon thought experiments that feel safely distant. The ISS data closes that distance. Dramatically, the station is not exotic. It is a low Earth orbit platform that has been continuously occupied since November 2000. It is close enough that on a clear night, you can see it moving across the sky with the naked eye, a bright point drifting steadily through the stars. Hundreds of crew members have lived and worked aboard it, and every single one of them, for every single day they were up there, was experiencing time at a slightly different rate than everyone they left behind. The atomic clocks confirm it. The equations predicted it. The measurements match. It is not a rounding error. It is not a sensor glitch. It is time dilation, playing out in the bones and blood of human beings. In March of 2015, astronaut Scott Kelly launched to the International Space Station for what would become a nearly year-long mission. He was not the first person to spend extended time in orbit. He was not even the most experienced astronaut alive. But he had something no other long-duration mission subject had ever had waiting for him back on Earth. An identical twin. Mark Kelly, also a former NASA astronaut, stayed on the ground for the entire duration. Same DNA, same upbringing, same biological starting point. And for 340 days, the universe ran 2 completely different clocks for them. NASA recognized what this situation represented almost immediately. The agency formalized it into one of the most ambitious human research studies ever conducted under the heading of the twin study. The goal was straightforward in concept and enormously complicated in execution. Track every measurable difference between two genetically identical people, one of whom had spent nearly a year in low Earth orbit, and one of whom had not. Dozens of research teams worked on different corners of the problem: gene expression, telomere length, cognitive performance, microbiome composition, vision changes, fluid distribution in the body. The study was, by any measure, comprehensive, but underneath all of that biology, there was a physics question quietly running in the background, one that had a clean, calculable answer. Scott Kelly, during those 340 days, was moving at roughly 28,000 kilometers per hour. He was also sitting higher in Earth's gravitational field than his brother. Both of those facts have consequences for time. Special relativity says a clock moving at that speed ticks measurably slower than a clock sitting still. General relativity says a clock in weaker gravity ticks measurably faster. These two effects push in opposite directions. The velocity effect wins. The net result is that time on the ISS runs fractionally slower than time on Earth's surface. Not by much, but by a precise, calculable amount. Over 340 days, Scott Kelly lived through approximately 5 milliseconds less of the universe than Mark did. He aged, by the clock, that much less. 5 milliseconds. That number sounds trivial. It is smaller than the blink of an eye. It would not register on any scale a person could perceive without instruments. But that is not the point. The point is that it is real. It is not a rounding error. It is not a limitation of the measurement. It is what the equations of general and special relativity predict, down to the precision that atomic clocks can verify. Scott Kelly returned to Earth on March 1st, 2016, genuinely, physically, measurably younger than his twin brother, by a margin so small that biology cannot detect it, but by a margin that the universe absolutely kept track of. Were we watching two people who had started life at the same moment diverge across time? In the most literal sense, yes. Two men born on the same day, carrying the same genetic blueprint, who had now accumulated different amounts of elapsed time in their bodies. Not because one of them had done something unusual to the fabric of space, simply because of where each of them had been. The universe does not ask permission before it runs separate clocks for separate observers. It just does it. The biological data from the twin study told a more complicated story than the physics did. Scott's telomeres, the protective caps on the ends of chromosomes, often used as markers for cellular aging, actually lengthened during his time in space, which surprised researchers. They shortened again after he returned to Earth. His gene expression showed thousands of differences compared to Mark's, with the majority returning toward baseline within months of landing. His cognitive performance showed some measurable decline. His microbiome shifted significantly and then partially recovered. The picture that emerged was not simple. Space changed Scott Kelly in ways that were real and significant, and in some cases, still not fully understood. But the time dilation element was different from all of that. It did not shift back after landing. It did not recover or reverse. Those 5 milliseconds stayed missing. The clock had run, the difference had accumulated, and that was final. There is something worth sitting with in that. The biological changes were dramatic and interesting and mostly reversible. The time difference was tiny and unremarkable and permanent. The universe is not dramatic about what it does with time. It simply does it, quietly, continuously, while no one is watching. Two brothers on separate paths through space-time, one of them circling the Earth 16 times a day at tremendous speed, and the universe keeping its own account of every second that passed for each of them, with perfect accuracy, without being asked. What the twin study gave scientists was not a spectacular result. No headlines screamed that Scott Kelly had returned from the future. Nothing visible or dramatic had changed about him that could be traced to time dilation. But it gave them something more durable than a dramatic result. It gave them a human face for a phenomenon that had previously lived almost entirely in equations and thought experiments. Einstein's relativity predicts that motion and gravity alter the passage of time. The Haffel-Keating experiment confirmed it with atomic clocks on airplanes. GPS satellites confirm it every day in the arithmetic that keeps navigation systems accurate. But Scott and Mark Kelly confirmed it with people, with two brothers, with 340 days of lived experience that left one of them fractionally behind his twin in the forward march of time. The study is still being analyzed in some of its dimensions. The long-term health implications of a year in space continue to interest researchers, and Scott Kelly has spoken publicly about lingering effects he noticed after returning. But the physics settled cleanly. The math said Scott would be younger by roughly 5 milliseconds. The measurements agreed. Nobody was surprised exactly. They were just reminded that this was not abstract anymore. The difference was real, physically measurable, and it told a story about what the universe does to time that no textbook had ever made quite so personal. Here is where the picture gets more complicated. Scott Kelly came back from space genuinely younger by a measurable margin. Fewer seconds had passed for him than for his brother. The physics on that point is settled and clean. But there is another question, a harder one, and it has nothing to do with clocks. What does the space environment actually do to the body over the course of a mission like that? The answer is unsettling in a way that no atomic clock can capture. Start with the most basic fact of microgravity. The human body evolved under one consistent pressure across millions of years. Gravity pulled down. The heart pumped upward against it. Bones bore weight. Muscles braced constantly against the planet's pull. Remove that force entirely, and the body does not celebrate. It begins, quietly and systematically, to come apart in ways the body was never designed to reverse. Fluid redistribution happens almost immediately. Without gravity pulling blood and lymphatic fluid toward the legs and lower body, everything migrates upward. The face swells. Astronauts describe a persistent feeling of fullness in the head, a slight pressure behind the eyes that never quite goes away. The legs thin out because they are no longer holding the fluid load they were built to carry. This is not uncomfortable in a dramatic way. It is just wrong, in the precise biological sense that the body's systems are responding to inputs they were never supposed to receive. The visual system bears the brunt of this pressure in ways that researchers have only recently begun to understand fully. Increased intracranial pressure from fluid migration causes the optic nerve to swell. Some astronauts experience degraded vision during long missions, a condition called spaceflight-associated neuroocular syndrome. The effects can persist for months after return to Earth. The eyes that come back from orbit are not quite the same as the ones that went up. This is particularly concerning for future deep space missions, where visual acuity may be critical for mission success or emergency procedures. The vestibular system, seated deep in the inner ear, registers gravitational orientation and spatial position. In microgravity, it receives no consistent signal. The brain must retrain itself to navigate space without these inputs, and astronauts experience persistent disorientation, spatial confusion, and motion sickness that can last weeks into a mission. The coordination systems that took years to develop through childhood grow unreliable. Walking, balance, and basic spatial reasoning require relearning upon return. Bone loss follows. In space, the skeleton stops registering mechanical stress because there is no weight to carry. The bones read this as a signal that they are no longer needed at full density. They shed mass at a rate that, in a person on Earth, would be flagged as severe osteoporosis. In longer missions, astronauts can lose several % of their bone density. Some of that returns after they land. Not all of it. The skeleton that comes back is not quite the same as the one that left. Similar forces act on the muscles. Without gravity to push against, they atrophy faster than any exercise program aboard the station can completely compensate for. The heart is a muscle. In space, it no longer has to drive blood upward against gravity, and it responds accordingly. It shrinks, it weakens. Returning astronauts sometimes struggle to stand for the first few minutes after landing, their cardiovascular systems temporarily unequal to the demands of a planet. Then there is the radiation. This is the piece of the picture that unsettles researchers most. On Earth's surface, the planet's magnetic field deflects the majority of high-energy cosmic radiation. Inside the ISS, that protection is reduced but still present. Beyond low Earth orbit, it is essentially gone. Cosmic rays are not the soft light of the visible spectrum. They are high-energy particles accelerated to near-light speeds by the same supernovae and black hole systems discussed in earlier sections. When they pass through biological tissue, they do not stop. They slice through cells, breaking chemical bonds, fragmenting DNA strands, triggering oxidative stress at the cellular level. The body can repair some of this damage, not all of it. The cumulative risk is real. Long-duration missions beyond Earth's magnetic shelter carry cancer risks that no current shielding technology eliminates. Scott Kelly was in low Earth orbit, inside the relative protection of Earth's magnetic field. Even so, radiation exposure on the ISS runs at roughly 10 times the rate experienced on the surface. Over 340 days, that accumulates. The twin study measured it. Kelly's telomeres, the protective caps at the ends of DNA strands, which shorten as cells age, showed measurable changes. Some lengthened during flight, which confused researchers initially. Then most of them shortened rapidly after he returned. His gene expression patterns shifted in ways that were still partially detectable years later. The body remembered what it had been through. The circadian rhythm, that ancient biological clock calibrated across evolutionary time to the 24-hour spin of the planet, receives no reliable signals in orbit. The ISS circles Earth every 90 minutes, producing 16 sunrises and sunsets per day. The body's sleep-wake cycle, controlled by light exposure and supported by systems that evolved under a single predictable cycle, collapses into fragmented patterns. Astronauts report sleep disruption throughout long missions, and the cumulative fatigue adds stress to every other system fighting against the space environment. This is not mere discomfort. Sleep deprivation carries measurable cognitive costs and suppresses immune function At the moment when the immune system already struggles against microgravity-induced changes in white blood cell behavior, there is also the question of the spine. Without gravity compressing the vertebrae, the cartilage between them expands. Scott Kelly returned from his year in space roughly 2 inches taller than when he left. This sounds like a minor curiosity. It is not entirely benign. The expansion puts pressure on nerves, and some astronauts experience significant back pain during missions for exactly this reason. Within days of landing, gravity reasserted itself, and Kelly shrank back to his normal height. The spine compressed. The adjustment was not painless. None of this is exotic or theoretical. These are documented, measured, catalogued effects that happen to every astronaut on every long mission. The bodies that come back from the ISS are not the same bodies that went up. They have been processed by an environment they were not built for, and the damage runs deeper than any benefit the clock physics can provide. Here is the full shape of the paradox. Take the twin scenario, the one that demonstrates time dilation so cleanly. The traveling twin returns younger. That is true. By milliseconds, by a real margin that atomic clocks confirm. In the strict physical accounting, fewer seconds elapsed for the person who traveled. But run that same person through a year of microgravity, chronic radiation exposure, fluid redistribution, bone loss, cardiovascular remodeling, disrupted sleep cycles, and the grinding psychological weight of isolation from every natural environment they evolved alongside. And what you get is not a younger person in any meaningful biological sense. You get someone whose body has been aged in ways the clock does not see. The universe offers you the narrowest possible discount on time, milliseconds, and it charges you for it in bone density, DNA damage, muscle mass, and cardiovascular function. The trade is not favorable. No rational biology would sign that contract. Technically younger by milliseconds, biologically older in ways that took years to fully catalogue. The universe has a sense of irony. Everything discussed so far involves small differences. A few microseconds drifting on a satellite clock. 5 milliseconds shaved off a year in orbit. Fractions so small that no human nervous system could ever perceive them directly. They only become visible when you press an atomic clock up against the mathematics and watch the numbers diverge. But there is a class of object in the universe where this changes entirely, where the fractions stop being fractions, where time dilation is not a correction you need sensitive instruments to measure. It is something you could, in principle, watch happen from a safe distance, if you were close enough and fortunate enough to survive the neighborhood. Black holes are where the story stops being subtle. A black hole forms when a massive star collapses at the end of its life. The core implodes. The mass that was once spread through a star the size of a small city's orbit gets compressed into a region so small that the curvature of space-time around it becomes catastrophic. The defining feature is the event horizon, a boundary in the geometry of space beyond which nothing, including light, can return. The mass itself may occupy something approaching a single point. What surrounds that point is a region of space-time so warped that every path through it leads inward. But long before anything reaches the event horizon, the gravitational time dilation becomes severe. To understand the scale of what happens near a black hole, you need one number: the Schwarzschild radius. This is the radius at which any mass, if compressed tightly enough, would become a black hole. For the Sun, It is about 3 kilometers. The Sun is not a black hole, so this is a theoretical boundary, but it gives you a reference. For a stellar mass black hole of around 10 solar masses, the Schwarzschild radius is roughly 30 kilometers. The event horizon sits at that distance from the center. Everything inside that 30-kilometer boundary is gone from the observable universe. The Schwarzschild radius scales linearly with mass. A supermassive black hole at the galactic center, containing millions or billions of solar masses, has a Schwarzschild radius that extends to millions of kilometers. This means the strength of time dilation at a given distance from the event horizon depends directly on the mass and density of the collapsed object. Near a stellar black hole, the gradient of space-time curvature is extreme over small distances. Near a supermassive black hole, you might drift far from the event horizon before encountering the most severe effects. The physics remains identical in both cases, but the geometry of space-time warps differently depending on what mass created the curvature. Now, stand back. Place yourself at a distance of 10 Schwarzschild radii from that black hole. You are 300 kilometers from the center. You are not crossing any boundary. You are not in immediate danger of being pulled in, assuming you have sufficient thrust to maintain position. But your clock is already running slower than the clock of someone watching from far away. At 10 Schwarzschild radii, gravitational time dilation causes time to pass roughly 5% slower than it would for a distant observer. Not 5% of a microsecond, 5% of every second, every minute, every hour. Sit there long enough, and the difference becomes hours, then days, then years. Move closer. At 5 Schwarzschild radii, the effect doubles. Time is running noticeably slower relative to the distant observer. At 3 Schwarzschild radii, you are approaching the innermost stable circular orbit for a non-rotating black hole, the closest path on which matter can orbit without spiraling inward. Here, gravitational time dilation is severe. For every second you experience, roughly 2 seconds pass for someone watching from a safe distance. An hour near that orbit is 2 hours elsewhere. A year is 2 years. Were you watching a star die in real time? The question astronomers asked about Betelgeuse is almost gentle compared to what you would be asking here. At 3 Schwarzschild radii from a black hole, you are asking a different question. How many years have passed back home? Move to twice the Schwarzschild radius. You are 60 kilometers from the center of that 10 solar mass black hole. The effect is dramatic. Time for you runs at roughly 60% of the rate of time far away. For every 10 hours you experience, 16 pass elsewhere. The distortion is no longer a correction. It is the dominant feature of your experience. Gas, dust, and debris that orbit in this region, swirling in what astronomers call the accretion disk, experience this time distortion continuously. Every particle circling that close is living on a clock that runs slower than anything on the ground floor of any building on Earth has ever run. This matters for real physical systems, not just thought experiments. Accretion disks around black holes are among the brightest objects in the universe. Material falling inward releases enormous amounts of energy. The inner edge of the disk, where matter spirals down toward the horizon, is where gravitational time dilation is strongest. Radiation emerging from those inner regions carries the signature of that distortion. The light is redshifted, stretched to longer wavelengths, because it is climbing out of an extreme gravitational well. Astronomers can look at the spectrum of light from a black hole's accretion disk and read the time dilation directly from the color of the light. The physics is not theoretical in those observations. It is sitting there in the data, matching Einstein's equations. For anything unlucky enough to orbit close to a stellar mass black hole for an extended period, the accumulated time difference against the outside universe is staggering. Take a hypothetical object orbiting just outside the innermost stable orbit for 10,000 years by its own clock. The universe outside has aged significantly more. Not a rounding error. A genuinely different elapsed time for the same physical duration lived in two different places. This is not metaphor. It is the prediction of general relativity, and the measurements of real systems near real compact objects have verified it with extraordinary precision. Binary systems containing black holes or neutron stars have been used as precision laboratories for exactly this reason. The timing of signals from these systems encodes the gravitational and velocity-based time dilation experienced by material orbiting in the extreme environments near collapsed stars. Every measurement comes back consistent. The math holds. The warping of time near massive compact objects is not a theoretical edge case. It is a feature of how these systems actually work, encoded in the signals they send across the galaxy. There is something deeply strange about sitting with this. GPS satellites require a correction of 38 microseconds per day, and that correction feels significant given how much modern technology depends on it. But 38 microseconds is barely a rounding error compared to what happens near a black hole. The difference between those two regimes is not just one of scale, it is a difference in kind. Near Earth, time dilation is a subtle tax on precision instruments. Near a black hole, it is a restructuring of what the word simultaneously even means. A clock near a stellar mass black hole does not need to be read with atomic precision to show its discrepancy against a distant observer. Given enough time, the divergence accumulates into something that would register on an hourglass. Given enough proximity and enough elapsed time, it accumulates into something that would register in the difference between a civilization and its ruins. Near a black hole, the effect is not a matter of microseconds. It is a matter of whether time, from a distant observer's perspective, appears to move at all. The event horizon of a black hole is not a surface you can touch. There is no wall, no membrane, no visible edge hanging in space that you could reach out and press your hand against. It is a boundary defined entirely by geometry, the precise distance from the center at which the curvature of space-time becomes so extreme that escape requires moving faster than light. And since nothing moves faster than light, nothing escapes. The event horizon is not a place, it is a threshold, a point past which the mathematics of general relativity say time and space have traded roles so completely that all paths, every possible direction you could travel, lead inward. That alone is strange enough, but what happens to time at the event horizon is stranger still. Imagine watching from a safe distance. A spacecraft is falling toward a black hole. From where you are observing, something begins happening almost immediately. The spacecraft appears to slow, not because it is actually decelerating. Nothing is pushing against it. It is falling freely, accelerating under gravity, just as anything would. But from your perspective, its movements become progressively more sluggish. The crew inside, if you could see them, would appear to move in slow motion. Their instruments would appear to tick more and more slowly. Their clocks, if you could read them from this distance, would appear to run slower with every passing moment. This is gravitational time dilation at its most extreme, and it is not an illusion of distance. It is what time is actually doing near that much mass. Now watch what happens to the light coming off the spacecraft. As it falls deeper, the light it emits has to climb out of an increasingly deep gravitational well to reach you. Climbing out of a gravitational well costs energy. For light, energy is frequency. The higher the frequency, the more energy the photon carries. When a photon loses energy climbing out of gravity, its frequency drops. Its wavelength stretches. This is gravitational redshift, and near a black hole, it becomes extreme. The light from the falling spacecraft shifts from white to yellow, then to orange, then to deep red, then to infrared. The signal dims as the photons arrive farther and farther apart in time. Dimmer and redder with every meter of descent. As the spacecraft approaches the event horizon itself, the redshift approaches infinity. The light takes longer and longer to escape. From your position watching, the spacecraft appears to slow to nearly a halt. It does not cross the horizon. It crawls toward it asymptotically, growing dimmer and more red with each passing second, until it has faded below any threshold of detection. From your perspective, the spacecraft never crosses. The clock on board, as seen from where you stand, appears to stop. Time for the falling object, measured by you, has effectively frozen at the boundary. This is the visual manifestation of time dilation becoming infinite. At the event horizon, the math says the dilation factor reaches infinity. A clock falling in would appear, from outside, to tick infinitely slowly. Infinitely slowly means not at all. Now switch perspectives. What does the person inside the spacecraft actually experience? Nothing dramatic. That is the answer. And it is one of the most unsettling things general relativity tells us. The infalling observer feels no great force at the moment of crossing the event horizon of a sufficiently large black hole. There is no wall of fire, no physical sensation of passing a boundary. Their own clock runs normally from their own frame of reference. The light inside the spacecraft behaves exactly as it always does. They check their instruments, they breathe, their heart beats, their thoughts proceed at a completely ordinary rate. They cross the event horizon in a finite amount of their own proper time and feel nothing unusual at the moment of crossing. For them, the event horizon is not a dramatic moment. It is just another point in space, distinguished only by what becomes impossible on the other side of it. But here is the problem. Once inside, every signal they send back out never arrives. Every photon they emit toward the outside universe is caught in space-time geometry, so curved that its path simply cannot lead outward. The signals fall inward along with everything else. From their perspective, they can still receive signals from outside. The universe outside the horizon is still visible to them, in a distorted and increasingly compressed form. But they can send nothing back. The communication is permanently severed the moment they cross. This produces what looks, from the outside, like a paradox. The outside observer never sees the crossing happen. The infalling observer crosses in finite proper time. Both are correct. Neither perspective is wrong. What resolves the apparent contradiction is simply the behavior of light. The last photon the falling observer sends just before crossing takes an infinite amount of your time to reach you. Every photon sent after crossing never reaches you at all. So from your position, you receive a stream of increasingly redshifted, increasingly delayed signals from just before the crossing, spread out over what is technically an infinite duration. The image of the spacecraft lingers at the horizon, fading, cooling, dimming, frozen in your sky. Two physically real, internally consistent descriptions of the same event, completely incompatible pictures of what happened, both of them true. Now consider what this means for the accumulated time difference. A clock hovering just outside the event horizon, held there by some enormous engine fighting against the gravitational pull, would run extraordinarily slowly compared to your clock far away. The closer it hovers to the horizon, the more slowly it runs. At 1 Schwarzschild radius above the horizon, the distance equal to the radius of the horizon itself, the time dilation factor has already become dramatic. A clock there might tick once for every many ticks of your clock at a safe distance. Closer still, the ratio grows without limit. The proper time experienced by something hovering near the event horizon is almost nothing compared to the time experienced far away. This is not gradual. The relationship between distance from the horizon and time dilation is not linear. It steepens sharply as you approach. Most of the extreme dilation is packed into the final stretch, the last few radii of approach. A clock sitting at twice the Schwarzschild radius runs significantly slower than one at 10 times that distance. A clock at 1.5 times the Schwarzschild radius runs dramatically slower still. By the time you are hovering just above the horizon, the curve has gone nearly vertical. Time outside is running away from you. Months pass out there for every moment you experience. The practical consequence for anything unlucky enough to orbit very close to a black hole is that time passes more slowly there and never catches up. An object locked into a tight orbit around a stellar mass black hole at close range would accumulate a time deficit relative to the surrounding universe that grows without stopping over the lifetime of the system. If that orbit held for 1 billion years of outside time, the clock in the orbit would register something far less. How much less depends on how close. How much less approaches zero as you approach the horizon. What light does at the event horizon is the clearest way to see what time is doing there. Light carries information. Information is what the outside universe can know about events. At the event horizon, light emitted outward is trapped. It neither escapes nor moves inward. It simply hangs, suspended in the geometry. Photons aimed directly away from the black hole at the event horizon go nowhere. They are stationary in space, which means all of their motion through space-time is being consumed entirely by motion through time. And even then, they cannot climb out. This is the point at which the structure of space-time has been warped so severely that the concept of outward stops meaning what it means anywhere else in the universe. The infalling observer passes through this without feeling it. Their local space-time remains well behaved. The horizon is not a place where physics breaks down for them. It is just the universe outside that has become unreachable. They still experience time. They still age. They simply can no longer tell you about it. From where they stand, they have already fallen in. From where you stand, they never will. Black holes are not the only objects in the universe with extreme gravitational time dilation. When the discussion turns to warped space-time and frozen clocks, black holes tend to absorb all the attention. That is understandable. They are the most dramatic objects general relativity predicts, but they have a practical problem as observation targets. You cannot see them directly. You infer them from what they do to surrounding matter, the light that bends around them, the gas that spirals in. The extreme time dilation effects near an event horizon are real, but testing them with precision is not easy when you cannot point a telescope at the thing directly. Neutron stars are different. They are visible. Some of them announce themselves across the galaxy with a regularity that makes atomic clocks look sloppy. A neutron star forms when a massive star collapses. The core, left behind after the outer layers explode away in a supernova, is crushed by its own gravity into something almost unimaginable. The entire mass of the Sun compressed into a sphere roughly 20 kilometers across, the diameter of a city. At that density, individual atoms no longer hold together. Protons and electrons are forced into each other, forming neutrons packed edge to edge. A single teaspoon of neutron star material, transported somehow to Earth, would weigh roughly 1 billion tons. Gravity on the surface runs at about 100 billion times the surface gravity of Earth. Stand on a neutron star, and a feather and a cannonball are the least of your concerns. The neutron star would be the last thing you ever stood on. At that gravitational intensity, time dilation is not the tiny whisper it is on the ISS. It is a measurable difference that accumulates in ways that precision instruments can track across years of observation. A clock on the surface of a neutron star would run noticeably slower than a clock held at a safe distance in space. Not by microseconds, by a fraction significant enough to matter in the calculations of orbital mechanics. This is the kind of extreme that general relativity was built to describe, and neutron stars are one of the few places in the universe where those descriptions can actually be checked. Some neutron stars spin, some spin fast, some spin so fast they rotate hundreds of times per second, sweeping beams of radio waves around like a cosmic lighthouse. These are called pulsars, and their pulses arrive at Earth with a precision that rivals the best clocks ever built. For physicists looking to test general relativity, a pulsar is not just a strange object, it is a tool. The real opportunity came when astronomers found pulsars that were not alone. Binary pulsar systems, two neutron stars in close orbit around each other, are where the physics becomes extraordinary. Each star contributes its own gravitational field. Both are moving fast enough in their orbits that special relativistic time dilation from velocity is significant. The combination means that the timing of the radio pulses the pulsar sends out is affected by both types of time dilation simultaneously, exactly the situation Einstein's equations were designed to describe. In 1974, Russell Hulse and Joseph Taylor discovered the first such binary pulsar, now designated PSRB 1913+16. Two neutron stars orbiting each other, one of them a pulsar, completing a full orbit roughly every 8 hours. The orbital speeds involved are a significant fraction of the speed of light. The gravitational fields are intense. Everything Einstein predicted should be happening to time in that system, and Hulse and Taylor had the precision tool, the pulsars ticking, to measure it. What they found matched the predictions of general relativity with an accuracy that stunned the physics community. Every detail of the pulse timing, the way it shifted as the pulsar moved toward and then away from Earth, the way it changed over months and years, was consistent with Einstein's equations down to the measurement limit. But there was something else. Something the observations revealed that went beyond time dilation itself. The the two neutron stars were slowly spiraling toward each other. Their orbital period was shrinking. The gap between them was tightening at a rate of about 3.5 meters per year. General relativity predicted this would happen because two massive objects orbiting each other in curved spacetime should radiate energy in the form of gravitational waves, and as energy bleeds away, the orbit decays. The rate of decay that Hulse and Taylor measured matched Einstein's predictions to better than 1 part in 1,000. Gravitational waves had never been directly detected at that point. This was indirect evidence, but it was evidence so precise and so consistent that it was treated as confirmation. Hulse and Taylor received the Nobel Prize in 1993. The decay of that orbit, measured through the timing of pulsar pulses, remains one of the most rigorous tests of general relativity ever performed. Other binary pulsar systems have since been found. The double pulsar system J0737-3039, discovered in 2003, gave astronomers both objects actively pulsing, two clocks in each other's gravitational fields, orbiting at close range. The measurements of time dilation from that system have confirmed general relativity at the level of 0.05% accuracy. These are not cosmological abstractions. They are experiments running continuously, out in the galaxy, producing data that any radio telescope array can collect on a quiet night. The objects themselves are strange enough to belong in a different kind of physics. More mass than the sun, narrower than a city, spinning hundreds of times per second. Gravity so intense, it reshapes space-time in a measurable way at every point in the surrounding volume. And yet, because of the pulsar's beam, because of the clock they carry embedded in their rotation, astronomers can measure what time is doing around them with extraordinary precision. A neutron star is compact enough to fit inside a city, and if you stood on its surface, time would pass measurably slower than for anything orbiting at a distance. Not by microseconds, but by an amount a clock could show. The implications of time dilation for long-distance space travel are not theoretical. They are waiting. The moment humanity attempts to cross interstellar distances at anything approaching a meaningful fraction of light speed, the equations stop being background physics and become the central engineering problem of the mission. Not propulsion, not life support, time itself. Start with the distance. Alpha Centauri, the nearest star system to our own, sits roughly 4.37 light-years away. That number sounds manageable until you put it against actual spacecraft speeds. The fastest human-made object ever launched, the Parker Solar Probe at its peak, travels at around 0.006% the speed of light. At that speed, a one-way trip to Alpha Centauri would take approximately 73,000 years. The crew roster would need to extend across several hundred generations. This is not a mission. It is a civilization migration with no guarantee of arrival. To make interstellar travel anything other than a multi-generational tragedy, you need to close that gap dramatically. You need to approach a significant fraction of light speed. And the moment you do, time dilation stops being a subtle correction and becomes the defining reality of the journey. At 90% the speed of light, the Lorentz factor is approximately 2.3. What does that mean in practice? A trip to Alpha Centauri that takes roughly 4.9 years by Earth clocks would feel like about 2.1 years to the crew aboard the ship. That is not a negligible difference. The crew ages 2 years. Earth ages 5. They return to find children who were toddlers when they left are now starting school. The gap is real. It is permanent. There is no getting those years back on either side. But 90% the speed of light is still modest by the standards of what the equations allow. Push to 99% the speed of light, and the Lorentz factor climbs to roughly 7. Now the calculus changes dramatically. A journey to a star 50 light-years from Earth takes 50 years as measured from the ground. From inside the ship, the crew experiences about 7. They depart, they travel, they arrive, and they have aged 7 years. Meanwhile, every person they knew on Earth has aged half a century. Parents are elderly or gone. Children are middle-aged. The political situation, the cultural landscape, the names of things, all of it has moved forward 50 years without them. They are not returning home. They are arriving at a place that used to be home and has since become something else entirely. Now consider 99.9% the speed of light. The Lorentz factor at that velocity is approximately 22. A mission to a star system 500 light-years out, which might be chosen for its potentially habitable planets or its scientific interest, takes 500 years from Earth's perspective. The crew experiences roughly 23. They spend 2 decades in transit, do their work, and turn the ship around. By the time they complete the round trip and decelerate back to Earth, more than 1,000 years have passed on the ground. Every institution that funded the mission has dissolved, reformed, dissolved again. Every language they grew up speaking has drifted or died. The civilization that sent them may not exist in any recognizable form. Were they still a crew at that point? What mission are they returning to complete? These are not philosophical distractions. They are genuine operational questions that any civilization attempting this kind of travel would have to answer before the launch window opens. The challenges multiply when considering the irreversibility of the commitment. A civilization sending such a mission accepts that it will likely never receive substantive updates from the crew again. Communication sent years into the journey reaches an Earth that has already reacted and changed course. The crew cannot shape decisions at home or influence the civilization's development. This asymmetry is complete. Mission parameters must be defined with extraordinary precision before launch, knowing there can be no course corrections based on what humanity discovers after departure. The crew commits irreversibly to their path through both space and time, utterly isolated and finally alone. This is the straightforward prediction of special relativity. It is not speculative. The same equations that required GPS engineers to pre-tune satellite clocks before launch, the same physics confirmed by cesium clocks flown around the world on commercial aircraft, extended to their logical conclusion at extreme velocities, produce these numbers. The physics has been tested at every accessible scale. There is no reason to think it breaks down at higher velocities. If anything, the evidence points in the opposite direction. What changes at interstellar scales is not the physics. It is the human weight of what the physics produces. An astronaut returning from 6 months on the ISS has lost 0.005 seconds relative to people on Earth. That is a curiosity. A crew returning from a 99.9% light speed mission to a nearby star has lost decades relative to the civilization that sent them. That is a rupture. The same mechanism, scaled up by the relentless acceleration of the Lorentz curve, produces something categorically different in its consequences for everyone involved. There is something else worth considering. The crew does not feel time passing strangely. This is the part that is hardest to hold in mind. Inside the ship, clocks run normally. Conversations happen at normal speed. Coffee cools at normal speed. Cells divide at normal speed. From the crew's perspective, they are simply living their lives, crossing a distance, doing their jobs. The compression of time is not an experience they have. It is a fact that exists in the comparison between their clocks and the clocks left behind. They step off the ship feeling like they have been gone for 2 decades. The universe tells them it has been 1,000 years. Both are correct. Neither can be argued with. No technology resolves this. No communication system fixes it. Radio signals still travel at the speed of light, which means a message home takes centuries to arrive and centuries for a reply to come back. The ship is not just isolated by distance, it is isolated by time. The crew exists in a bubble of their own present moment, drifting forward through centuries they are not experiencing, surrounded by a universe that is aging around them at a rate they cannot perceive from the inside. Humanity has not built the propulsion system that would make any of this real. Current physics offers no clear path to 90% the speed of light for a crewed vessel, let alone 99.9%. But the question of whether it is possible someday is separate from the question of what it would mean if it were. And what it would mean is this. The moment a civilization sends people across interstellar distances at relativistic speeds, it is not sending explorers on a round trip. It is sending them forward through time. The crew departs one era and arrives in another. They return, if they return, to another still. The people who returned would be strangers to the era they had left, not because they felt any different, but because the rest of the universe had moved on without them. There is something deeply unsettling about what time dilation reveals, and it has nothing to do with the physics. The physics is strange enough, but underneath the equations, underneath the atomic clocks and the GPS corrections, there is a quieter problem. A problem that touches something most people have never thought to question. The assumption that we all share the same moment. That right now, everywhere, is the same right now. It isn't. This is not a poetic way of saying that people in different time zones see different sunrises. It is a precise, mathematical, experimentally confirmed fact about the structure of reality itself. Two observers moving at different speeds or sitting in different gravitational fields are not merely measuring time differently. They are genuinely living through time at different rates. Their clocks are not reporting different numbers because of calibration errors or instrument drift. The seconds themselves are passing at different speeds, and there is no outside referee, no master clock somewhere, to declare which of them is measuring correctly. Both are correct, for their own location, their own motion, their own path through space-time. This is what physicists mean when they say simultaneity is relative. Take two events happening at the same moment according to one observer. A flash of light on a train platform on the left and another on the right, timed so they appear perfectly simultaneous to someone standing at the center. Now watch that same scene from the perspective of someone moving past on a fast train. For that second observer, the flashes are not simultaneous. One arrives before the other. Not because of any travel delay, not because of the time it takes light to cross the platform. The events themselves, in their frame of reference, genuinely happen at different times. This follows directly from the requirement that light travels at the same speed for every observer. The math has no loophole. If the speed of light is constant, simultaneity cannot be universal. What does that mean for the present moment? Most people walk through life with a background assumption so deep they've never noticed it. The assumption that right now is a real thing. That somewhere, at this very instant, an astronaut aboard the International Space Station and a researcher at the bottom of a mine shaft in South Africa and a hypothetical traveler coasting at half the speed of light toward a distant star are all experiencing the same slice of universal time, the same cosmic now. It feels obviously true. It is not true. There is no universal now. The concept simply does not exist as a feature of the universe. What exists is your local now. The time your clock reads in your gravitational environment, moving at your speed, following your particular path through space-time. Physicists have a name for your personal experience of time along your specific path. They call it proper time. Every object in the universe accumulates its own proper time. Two clocks that start together and reunite after traveling different paths will show different accumulated times. Neither is wrong. Neither is ahead or behind in any absolute sense. They simply travel different roads through space-time, and those roads had different lengths in the time direction. Here is where it gets philosophically uncomfortable. Every experience you have ever had, every memory, every moment of waiting, every sense that the present is slipping away into the past, is not a report on a universal fact. It is a local measurement. Your brain, running its electrochemical processes at a rate set by your particular gravitational environment and velocity, is generating an experience of time that is specific to you. Someone else, moving differently, is generating a different experience that is equally valid. There is no version of reality where both of you agree, moment by moment, on what is happening right now across the universe. That said, the universe does not collapse into chaos. There is a feature that holds causality together even when simultaneity falls apart. Information cannot travel faster than light. This is not just a speed limit on spacecraft. It is the constraint that keeps cause and effect intact across a universe where observers disagree about the order of events. Two events can appear in different order to different observers only if no signal could have connected them. If one event could have caused the other, then every observer will agree on which came first. Relativity shuffles the deck on simultaneity, but cause always precedes effect. Always. This is what keeps physics from unraveling into a situation where an observer could see the answer before the question was asked. But that reassurance about causality does not fully close the philosophical wound. Because even if cause and effect stay ordered, the texture of time, the felt thickness of a second, the rate at which the future becomes the past, is not shared. Somewhere right now, if right now even means anything across cosmic distances, a clock near a dense stellar remnant is ticking at a rate meaningfully slower than a clock drifting through empty intergalactic space. Neither clock is malfunctioning. The universe is just built this way. The strangest part is how invisible this remains to ordinary human experience. Every person alive has the deep bodily intuition that time is a river, flowing at one constant speed, the same for everyone. That intuition has been wrong since Einstein published his first paper in 1905. We have known it was wrong, with experimental precision, since at least 1971. The correction runs quietly inside every GPS satellite. It has been measured in the bones of astronauts. It has been confirmed in atomic clocks flown on commercial aircraft. And still the intuition persists, because at human speeds and human altitudes, the differences are too small to feel. You will never feel your time running differently from someone else's, but it is, right now. The universe does not care what year you think it is. It runs on its own schedule, and your schedule is a local matter. Rise above the particulars and consider what time dilation is really telling us. Every time your phone locks onto a GPS satellite and drops a pin, engineers have already done something remarkable. They pre-tuned the clocks aboard those satellites before launch, bending them slightly out of rhythm so that once the satellites reached orbit, moving fast, sitting high in weaker gravity, the clocks would settle into agreement with clocks on the ground. That correction runs silently, invisibly, in the infrastructure of modern navigation. You never see it, but without it, the errors would stack up at roughly 10 kilometers per day until the system became useless. Einstein's equations are not running somewhere in a physics department. They are running in your pocket. That is what makes time dilation genuinely disturbing. It is not confined to thought experiments or the extreme conditions near collapsing stars. It is happening right now, at every altitude, at every speed, to every clock in existence. The atomic clocks aboard the International Space Station tick at a slightly different rate than the ones on the ground below. The difference over 6 months is about 5 milliseconds. That is not a measurement error. That is the universe running a different schedule for objects in different conditions, and it does so without exception, without pause, and without caring whether anyone is watching. What the atomic clock experiments revealed, Haffel and Keating flying cesium clocks around the world on commercial airplanes, NIST researchers measuring time differences between clocks 1 foot apart in elevation, is that this is not a special case phenomenon. It is the texture of reality. Every centimeter of altitude, every kilometer per hour of velocity, carries a small relativistic signature. The universe is not ticking in unison. It never was. Scott Kelly came back from 340 days aboard the ISS, having passed through measurably fewer seconds than his twin brother on Earth. Two people with identical DNA, born on the same day, are now not precisely the same age. The difference is small enough that no biological process could detect it without instruments. But it is real. The universe ran different clocks for them, based solely on where each of them happened to be. That is not metaphor. That is what general and special relativity predict, and that is exactly what the measurements showed. And then there are the black holes. Near the event horizon of a black hole, time dilation stops being a matter of microseconds. An object falling toward the horizon appears, from a safe distance, to slow. Its light redshifts. Its movements grow sluggish. At the horizon itself, it appears to freeze. From the outside, the infalling object's clock appears to stop entirely. The light it emits stretches toward infinite wavelength and never quite arrives. Whatever crossed over is gone from the observable universe in the most complete possible sense. That is what time dilation looks like when the gravitational curvature becomes extreme enough. It does not bend time. It ends it from where you are standing. The logic that produced all of this began with a single stubborn fact. The speed of light is the same for every observer, regardless of how fast they are moving. That constraint followed honestly to its conclusion unravels the Newtonian picture of time as a universal constant. It replaced that picture with something far stranger and far more accurate. Time is not a background. It is a physical quantity shaped by mass and motion, different for every object tracing its own path through space-time. Look up on a clear night. The light reaching your eyes from a bright star may have left its source 600 years ago. The star that emitted it has aged 600 years since that light departed, and you cannot perceive its current appearance. Some of those points of light are already gone. The news just has not arrived yet. Time is not a line you share with the things you see. Every object in the universe is running on its own clock, accumulating its own elapsed time along its own path, and the universe keeps no central record of how those paths compare. That is the disturbing truth. Not that relativity is complicated, not that the math is hard, but that time, the thing that feels most immediate, most personal, most undeniably real about being alive, is local. It belongs to you the way your position in space belongs to you. It is yours, and it is not the same as anyone else's. The clock is always ticking. It just does not tick the same way for everyone.